Good morning, everyone. I'm honored to have the chance to address you on this special occasion. My name is Zerui from Beijing University of Technology. The topic of my paper is Detection of HVDC Interference on Pipeline based on Convolutional Neural Network. Oil and gas pipelines are the medium used to transport oil and gas over long distance. They are buried deep in the ground, can be damaged from a variety of factors, especially the HVDC interference. The HVDC is called High Voltage Direct Current Transmission Line. It refers to the interference caused by the current released into the soil during the operation of the high voltage transmission system. The duration of such interference is short, but the soil potential change is very obvious, which will cause great damage to the pipeline. In this paper, based on the time series data generated by the smart test pair, we use one-dimensional convolutional neural network to detect the HVDC interference. The data in this study were taken from the real-time cathodic protection monitors of an oil and gas pipeline system. The data was obtained by the smart test pair for cathodic protection in order to detect the health condition of the pipeline in real time. A large number of smart test pairs are buried along the oil and gas pipeline, which are used to detect the potential current and the insulation performance of the pipeline. Each test pair is equipped with a wireless communication chip, which can transmit data to the server in real time through the Internet of Things, and then the server will analyze the transmitted data using machine and manual methods to find the possible interference problems in the pipeline. The collected data include pipeline potential, soil environment, pipeline current. Among them, the power-on potential and the power-off potential of the pipeline are sensitive to HVDC interference, so we use these two values as the main data sources for detection. These two figures is the typical curves of the pipe potential. Figure 1 is the potential after the interference of HVDC. Point A represents the beginning of the interference. C represents the peak. The B represents the end of the interference. Figure 2 is the potential curve without HVDC interference. The table is the sample size we used. In order to realize the effective analysis of data, we first clean the data and manually delete the obvious wrong data. These data are usually distributed discretely within the time range and have significant differences with the values of the surrounding moments. In addition, the test pair may send data repeatedly to the remote server, and we deleted the completely duplicated data. The data were marked by professionals in the way that the potential curve presented by the device was significantly offset. If HVDC interference occurred during a certain period of time, the data for this time range is labeled as characteristic data. In order to use the convolutional neural network to extract the feature of the data is segmented. Usually, the discharge time of HVDC transmission line is about 30 minutes to 4 hours, and a data is collected every 10 minutes. We used a random way to divide the time segments, starting from the first data after 0 o'clock every day. Every L data is divided into a time segment until the data of the day is clipped. The criteria is if the segment contains HVDC data, the segment will be marked as a positive sample, otherwise it will be marked as a negative sample. Finally, the data were artificially checked to eliminate the segments marked with obverse errors. According to different L, we can get different sample numbers. Here is the structure of one-dimensional convolutional neural network. The input feature vectors is the data to be analyzed. Convolutional layers is used to extract the local regional characteristic of input vector. After multiple convolutional operations and polling operations, the feature map is transformed into a feature vector by flattening or global polling. Multiple fully connected layers are used to further extract feature. The final output vector represents the result of the classification. Due to the small dimension of data to be classified, appropriate convolutional kernel and the layer number should be taken into consideration when designing convolutional neural network. A convolutional kernel of length 3 is used as the basic structure of the network. After every 2 convolutional kernels, the max polling layer is added. The number of the layers of the network is appropriately increased according to the length of the input sequence. In order to utilize the extracted features as much as possible, the feature map is transformed into one-dimension feature vector by using flattening operation. In order to improve the speed of the convergence, ReLU is used as the activation function in each layer. Here is the experimental result. There are 2 groups of potential data, power on potential and power off potential. It can be found from the result that the performance of the model on the power off potential is better than that on the power on potential, because the power on potential is affected by the protection current, and the characteristics of HVDC are relatively weakened. When L is considered, the best result of the experiment is when L is selected as 40. This is in line with our expectation, because as the length of the segment increases, the more data L contains, the more complete the segment containing HVDC data will be. When L exceeds 40, the accuracy data rate drops. It may be due to the decrease of data size. Secondly, we compare the one-dimension convolutional neural network with other classifier models. DTW and wavelet transform are common feature extraction methods in time series data classification. We choose segments with L equals 40 and use different classification methods to extract and classify the potential data. The results of the comparison are shown in the table. The experimental results show that one-dimensional convolutional neural network have better performance than DTW and wavelet transform. This indicates that convolutional neural networks can be selected as a HVDC interference detection method. In this paper, we built a one-dimensional convolutional neural network to classify HVDC, prove that one-dimensional neural network can be used to detect the pipeline potential timing series data. Power-off potential data can be more easily captured as a feature of HVDC. However, the current detection method is based on time sequence segments, and its sensitivity to time is not high enough. In the future, we will develop methods to achieve more accurate detection of HVDC. Thank you.